Hello everyone, welcome back to alkaline hydroxide 784, and today in the mathematics series we are finally going into section B, which is what you see in paper 2. And section B is what we call probability and statistics. And in the topic of probability and statistics, the first one that we will be covering is probability. So yeah, I've heard from I don't know many people that probability seems kind of hard, or I mean difficult, because hardness is probably more attributed to diamonds, I guess. But anyways, what's seemingly seems kind of easy on the surface is just like, oh, if you have this many objects, then just follow this rule. Actually can be quite difficult if you do not know how to approach the problem. It's kind of like physics. In physics you have like all the equations, and you think it's okay, once I know like what equation to use, I can do it like pretty easily, right? Yeah, that's true. But the problem lies in knowing which equation to use. That is where the difficulty lies. So likewise in probability, you need to know what are the techniques that you need to utilize to find the answer. And if you cannot identify all of them, and you don't identify all the different ways that the thing can be permuted, or whatever, or arranged, you will not find the answer, and you will end up saying, oh wow, probability is so difficult. So that's that in a that's how you usually that's the reason why you find probability difficult, maybe. But some of you might be like, huh, difficult, how is this difficult? I don't know. Yeah, if you find it easy, then good for you. That means you got it right. You know which what parts of like how to apply the probability. But at least Cambridge gives you a saving grace in the form of the first part of the question, which will always be some super easy question which involves some factorial, and then just find the answer using a factorial, and that's it. No complicated things to deal with. And it's only the subsequent parts that end up making it more and more complicated. So at least you can still get marks from the question. So please do those first parts at the very least. And maybe just scan through and see if there's any other part that they can actually still do, even though maybe there's one part you cannot do, like part B you cannot do. But part C you actually know how to do, then do it. Don't like leave it blank just because you thought, oh, the entire question will be hard because part B is hard or something. Look through it and do as many things as you can. And even try to do part B, even if it's wrong, it doesn't matter. At least you tried, and maybe you get method marks or something. It may be better than not getting marks at all by not actually doing the question. But of course, some people don't do the question because they didn't even have time to do the question, which I think we'll cover that later when it gets nearer to November. I will. Okay, it's actually already very near to November, but I will probably cover that in a separate episode or something. Time management, because I do realize that this series still has 5 more episodes after this, and so I cannot really finish everything in time for A levels. I also have things to do. I'm not a very free person. I'm doing this at Thursday. I'm recording this audio at like Thursday night. So yeah. Okay, so let's actually get into the topic. I think I talked too much. Okay, so for probability, the general idea is like physics. You need to know what are the different techniques that you can use for the questions. And in the question, you need to figure out which technique should be used. So what are the different techniques? I mean principles more of. I do not know what to call them, but you get the idea. So the first one is the addition principle, which is okay, actually that one is just the most generic way of approaching it. So let's say the probability of, I don't know, getting red is 3/5, and then the probability of getting 1/7. What is the probability of getting red or blue? You add them together, like because you can get red or blue. They do not like interfere with each other. They do not mix. Like it there is no influence of one color on the other. But for multiplication principle, which is the other principle, it usually is done when there's an influence on one thing, or when things are done in a sequential order. So let's say what is the probability of getting red twice or something like that? Okay, yeah, like let's say you replace the red and blue every time. So what's the probability of getting red twice? Then what you would do is you square 3/5, because you take red, you have a 3/5 chance of taking red. Then if you put it back in and then you try to take again, you still have a 3/5 chance of taking red. So you have to multiply it twice in order to make sure that you get red on both tries. That's the multiplication principle in a way. So yeah, that's the most generic way of approaching um probability, like it's like the overall umbrella in a way. So you need to go into more specific things that could change the probability. Okay, so the next part is about the concept of permutation and combination. So this is when okay, so let's just cover what the P and the C mean. uh, so permutation would be when you're trying to okay so for C, right, when you use C, you will just have the factorial. There is no division or no nothing. And what does that mean? Like, so if you have NCR, the N is the total number of objects that you have, and the R is the number of objects that you are arranging. So let's say you have 10 objects and you are arranging four, you are taking any four and arranging, like, combining them together. So um, in that scenario, you would um, you would just be like, okay, we have four objects out of 10, and in that, like, the combination isn't really about, it's just about picking any four out of the 10. So how do you do that? First of all, you get four, you can choose, imagine that you have 10 objects. Yeah, okay, fine. And out of the 10 objects, you can choose one. So let's say, for that you have a 1 in 10. Sorry, you have 10 choices. Then you choose the second object of the remaining 9 objects, and you have 9 choices. Then you have 8, and then you have 7. So if in the difference between combination and permutation is that permutation ends here, because if you think about it, the order of the object matters in permutation. So if you can choose 10 for the first choice, then 9 for the second, then 8 for the third, and then 7 for the fourth. But if it's combination, you don't need to worry about the order. So in this scenario, you need to remove all the different permutations of the order, because any selection of that order will still count as one of the combination. Like, will still, like, imagine if you chose a square, circle, triangle, diamond. No matter what order it will be, it'll all be counted as only one combination. Whereas in permutation, if you, let's say you have four of these objects, you can do so many permutations with that, and they will be counted as separate permutations instead of one single combination. Yeah. So in a permutation, in a combination, what you would do is yeah, okay. So for permutation, if you have your 10, 9, 8, 7, how do you express that in terms of n and r? So for n and r, what you end up doing is if you look at the 10, 8, 9, 7, you don't realize that it's actually 10 factorial, which would be 10, 8, 9, 7, 6, 5, 4, 3, 2, 1, all multiplied together, divided by whatever is below 7, the 6 factorial. So NPR is actually equals to n factorial over um, n minus r whole thing factorial. So in this scenario, we have 10 PR, that would be 10 factorial over 6 factorial. So 10p4, right? Because you're only choosing 4 objects. So 10 minus 4 will give you 6, and you can use that as your 10 factorial, or 6 factorial gives you your permutation. So let's say if you actually have all 10 objects and you do not need to worry about choosing only 4 objects or something, then you had to use all the objects, obviously. In a combination sense, this will just give you only one combination because you are using all of the 10 objects. But in permutation sense, what you can choose to order them in whatever different ways. Like you can choose which of the 10 objects to put first and which to put second, and you can do as many permutations with that. And how many exactly? It is 10 factorial. Because if we extend the thing that we said earlier about 10 choices, 9 choices, 8 choices, you extend it until 1, obviously it's just 10 factorial. And that's why the very first question is always like super easy. Be like, oh, I give you 5 objects, tell me how many ways there are to arrange these 5 objects. Like arrange, specifically arrange. Then obviously it's 5 factorial. And for any n objects, it will be n factorial. So that's how permutation works. So how do you do combination then? Combination is different because if we go back to our example of 4 objects, we we are only dealing with the selection of 4 objects out of the 10. We do not care about what order they are in. So how does that work? Let's say you have 10 objects. You can choose any 4 of them. How do you do it? Well, you could first do it in a particular order. Like say, you do what you do for your permutation. You have 10 times 9 times 8 times 7. But at the same time, you know that this is not the correct answer because there are many repeated combinations within this answer that you calculated. So you need to just remove all of the repeated combination. So you do the opposite of the multiplication kind of thing. You divide out all of the repetitions. And how do you do that? Well, if you think about the 4 factorial, right? Like you think about it as 4 factorial instead. That is the number of ways to arrange those 4 objects. So if you divide that from the 10 over 10 factorial over 6 factorial, that number, you will get your NCR. So in other words, your NCR is n factorial over r factorial times n minus r whole thing factorial. And that is the difference between the P and the C. Yeah. I hope you got this. I've probably written it down as well. Hopefully this makes sense. So let's move on. The next thing, I guess I'm being a bit too explainy on this particular topic. Most of the time I've just assumed that you know all the basic stuff. You should probably know, but I'm just explaining why this makes sense more than I'm teaching you what the basic stuff or something. I don't know. Okay, so the next thing is written here is arrangement of objects in a line or in a circle. So it will be including cases involving repetition and restriction. So we have covered the basic line scenario just now using the P and the C. I think I don't need to repeat this again, do I? So let's move on to a circle. Let's not do choosing the 4 out of 10. We'll just do it with 10 objects itself. So let's say you have 10 distinct objects. All of the objects are different. In the previous example, I also assumed that all of the objects are different. So yeah, just in case for your information. So all of the objects are different, and we can now arrange them in a circle. So what's the difference between a circle and a line? Well, a circle is technically a line. It's just connected to itself. That's the important part. It's connected to itself. The line has 2 ends. The circle doesn't really have like a cut end or something. It's just a continuous line in a way that closes up. So what does this mean? Imagine you have your 10 objects in a circle, and then you draw like a pentagon with them, a decagon with those 10, like joining the objects, like the vertexes of the decagon. And now that you have your decagon, you realize that there's 10, you can rotate it like 10 times to get back to the same point, and it'll be like some kind of a symmetry kind of thing. You can, there's like that many angles of axes of symmetry. And likewise, when you're doing your um a circle, you do realize that a circle that is slightly just shifted to the right still has the same arrangement. It's not like changed just because you shifted it to the right. But if you flip the entire circle over, it is a bit different because it's like stereoisomer in a way if you do that. But if you just rotate it, it will not change the arrangement in the circle. So yeah, in other words, you just need to do this one extra thing, which is to divide it by the number of people or objects in that circle. Yeah, that's all. That's all you need to do. If you see a circle, just take note of how many objects that you're actually accounting for in the circle and divide it by the number of those objects. I'll tell you more later when you're trying to do it groups, because that is a part where you tend to mess up the most. Because I'll just hopefully I'll actually remember to say that. Let me just drink some water. Okay, so now let's move on to cases involving repetition and restriction. So for repetition, it's very simple. If you see like two of the same thing, then you just put a 2 factorial underneath the thing. This for the simple reason that those two objects can be interchangeable. So you're basically like, you're just removing all the repeated arrangements that look exactly the same, even if when you swap those two objects. And when you have like 3 objects, you put 3 factorial because there's 6 different ways to arrange these objects, not just 3 but 6. And likewise, if you have an n number of similar objects, you divide the whole thing by n factorial. And there's multiple groups of similar objects, then you just do it for each of them individually. Like for example, you have like Mississippi, then you do one for the I, then you do one for the P, and one for the S. You get the idea. You count how many of each letter there is, and you make sure that all the repeated ones have the factorial divided out. Yeah. I think that made sense. uh, okay. What about restrictions? Restrictions, I guess, restriction is pretty broad, so it depends on the question. So the advice for this is to read the question, obviously. Usually like restriction will be like, oh, this thing cannot be in the front, or like this thing must be in the front. So let's say if they say there's this object that must be in a particular position, then for that position you can count it as only one choice. So this is in general, you can use this as a general method. If there's an arrangement of objects and there's some restrictions, and you don't want and you're a bit scared to like just write the factorial directly, you can instead, if there's not a lot of objects like 4 or 5, you can just draw like 4 or 5 dashes, and on top of each dash you can look at the number of choices you have for that object, for to put the object in that position. And once you have all of your numbers there, you can times them all together and you get your answer. It's as simple as that. So just think about it carefully. Don't misread the question or something. Read the question carefully, think about it properly, and then just do this dash method, and then you get your answer. Yeah. um and another kind of restriction isn't really about the object that can be placed or cannot be placed in a certain position, but more of like it cannot be placed next to some other object, or it must be placed with another object. So in the scenario where let's say you have two friends, I don't know, A and B, and these two people must be together no matter where you keep them in the line. You just put them as a group first, like just count A and B as one thing, and then you do the normal arrangement with the idea of A and B as one group instead of two people. And once you've accounted for the normal arrangement, you just look at A, and you can tell that A and B can either be A A on the right, B on the left, or A on the left and B on the right. And those are two different permutations. And you can just times the answer by 2 factorial after you're done with the permutation, counting A and B as a group. And likewise, if you have two people who cannot be to get next to each other, maybe A and B suddenly had a fight and then they don't like each other anymore. What do you do? Um, oh, okay. Yeah, so if you have A and B and they don't like each other and they do not want to be next to each other at any cost, you can, there's one way of doing it. You first find the ways where A and B are together. Then you just minus it from the total number of possible permutations where you don't care about A and B being together or not together. So like you can calculate A and B together, A and B not, like no condition, then you have A and B together, then you minus that from the no condition, and you get the condition where A and B must be separated. But the other way of doing it is that you can place A and B, and you can think of how many gaps there are between A and B. Um, you must realize that there's at least one gap in between them. And you can use that to figure out your arrangement. I think it's called the dot. There's the simple way of looking at it called the dots and cross dashes method. I do not remember it, but if you want, you can look it up if that helps. But if not, just do what I told just now, just to minus off the cases where they are together. But if it's something more complicated than that, then you have to really think about it properly, and then see what you should minus off or you shouldn't minus off. Yeah. Um, so the next part is the addition multiplication of probabilities. I think I just mentioned, I told it at the beginning itself, where you add and where you multiply. You add it when the two events do not influence each other. Like for example, the very first example I told was about the probability of getting red or blue. So there's no like, and there's no conditional probability here. It's not like you must get, like it's not like the getting red is gonna affect your probability of getting red or blue. Like there's no, sorry, what am I saying? Okay, never mind. Like you get the point. They're in the same scenario. There's no like extra condition added just because of a prior event or event later on. But multiplication is when you have more than one event subsequently, and the event before kind of helps to determine what happens afterwards or not. Yeah, so technically what I mean is that if you were to, not help determine the entire probability. The one where it helps determine what happens later is a bit more of the event that is not mutually exclusive. So in this scenario, the scenario that I gave at the beginning is mutually exclusive because you're replacing the red with and or the blue with every tick, and therefore the probability doesn't change, and so you just need to multiply it. But now if we move to events which are not mutually exclusive in a sense, um, you can look at it in terms of like one event influences the other. So let's say if you have 9 red counters and 4 blue counters in a bag, and you're not going to replace the counters at any point of time, so your probability of getting red is 9 over 13, and your probability of getting blue is 4 over 13. And the very first counter you take will affect your probability, will change the probability already. It becomes something over 12 instead of something over 13. And so when you're multiplying the probability, you have to take note of the changed probability. And one way of helping you understand what goes on is to draw tree diagrams, which I will cover very soon. But yeah, that's one way of helping you understand it. Yeah. So mutually exclusive is, yeah. events that don't really don't really do stuff to each other. They happen separately. Independent events is more of an event that is uh, oh sorry. Yeah, mutually exclusive. Sorry, I almost forgot what the meaning of mutually exclusive is. How brilliant. Okay, so mutually exclusive, it refers to events that cannot happen at the same time. So like that's what happens in the addition principle, the red or blue. You can't have both red and blue at the same time. You can't take a counter that is like some quantum particle that's suddenly red and then suddenly blue or something. It's not like that. This you're not looking at quantum physics here, so yeah, they're mutually exclusive events. The act of taking red or the act of taking blue. But but for independent events, which is what we look in the second example, like the second part where we are taking things one after the other, or you're replacing it and taking them again. That affects the independence of the events. So when you replace the counters, it is actually independent. So like the second, like the probability of taking the red on the second try will still be 3/5 if you replace the counter after taking out. But in the scenario where we had the 9/13 and all that, it will change to something over 12, and it's no longer independent in a sense. Yeah. Uh okay, so the next part is about what you can use to help you in your probability solving. Because honestly, if you were to try to think it in your mind, you'll just become like that lady from the meme who's just like staring into blank space with the maths equations all around her. You know what I'm talking about. And I think in probability diagrams are very helpful. Yeah. So what are the let me cover the different kinds of diagrams and we'll see where we can go from there. So a table of outcomes. Basically you just draw a table. You have like different outcomes on the table, let's say red, blue, green, something like that. And then on the second row you can write the probabilities of each of those outcomes or something like that. Yeah. And if you have more than one event, you can use one on the vertical, one on the horizontal, do other stuff. You get the point. A Venn diagram is you know what it is. It's all the circles that intersect each other, that kind of thing. The Venn diagram. And Venn diagrams can be pretty useful when you have a question that asks a really complicated restriction in the sense like it could be something like, oh, this person and that person cannot sit together, and that person and this person also cannot sit together, but these two people must definitely sit together. Like they tell you three or four of these things, then maybe a Venn diagram might help in that scenario. I don't know, it's very likely. Or when you're dealing with probability in terms of numbers, a Venn diagram will help as well. um like numbers, it's in they give you a bunch of events A, B, C, and then tell you the probability of them happening. Then they tell you whether they're mutually exclusive or independent. So in a Venn diagram, mutually exclusive would be it doesn't really affect how the circles wait. Like let's say you have two events, red and blue. The chance of red happening and the chance of blue happening. Yeah, sorry. Um, Basically, you have red and blue, and when it's mutually exclusive, red and blue do not intersect at all. So the intersection is zero. Whereas for independence, it's not really about the intersection being zero because both could happen, maybe both events could happen, but it's more like one event doesn't affect the other. So in this case, the Venn diagram may not help you, but the tree diagram will help you for that particular outcome. Uh, okay, sorry. The Venn diagram may help you if you know the equation of what happens when one event influences another. But if you're looking at it purely from a visual standpoint, then a tree diagram will be more useful. So for the tree diagram, the most obvious way you can use it is for stuff like the 9 red and the 4 blue. So you can first start with 9 over 13 probability of red and then 4 over 13 blue. Then you can separate it into the two outcomes, red or blue. And from there you can, if it's red, then obviously you minus 1 red and then you do calculation. Then you just branch it out again and again, and you can do it as many times as you need to for your question. And you can get an accurate way of calculating your probability. So let's say if you're trying to calculate the probability of getting a certain order of reds or a certain number of reds or blue, you just need to do the multiplication for each of the branches which is applicable to the question, and you just add up those probabilities, because each of those events that you multiply are like mutually exclusive, so you can add them up and you get your answer. Yeah. uh, I think this is not too hard. If you've had practice with it, you should know how to do it. Okay, so and then finally, yeah, the final thing is just permutation and combination techniques, which I've already explained to you. And I don't know how much time I've spent talking so far, so I don't want to talk too much. Okay, so the next part is calculation of conditional probabilities. Okay, conditional probabilities. This is what I was talking about. In other words, it's not independent. It's like the opposite of independence. So there's like one thing that is dependent on some other event happening, like the red and the blue tokens that we just mentioned in terms of the tree diagram. So just use a tree diagram or use your common sense to figure out the probability. I think it shouldn't be too hard, hopefully. Yeah, so the final point is the equations that you should probably know. For example, what is P of A prime? So okay, so let's say here we are using A and B as events, okay? And the best way to visualize these equations is in terms of a Venn diagram. And this is where you use a Venn diagram for a conditional probability. But if you're not using this terminology and you're just directly doing it, then a Venn diagram may not actually help you that much. This only if they give you some values of these particular terms beforehand. You can use a Venn diagram to help you visualize it. So A prime here is whatever is not A. Like, so A is a circle, then A prime is the stuff that is not that particular circle. So probability of A prime is obviously 1, because 1 is 100% minus the probability of A. So that's the first one, and I think that is clear enough. So the second one is the probability of A union B. So union means it can be either or, like, it can be A or B. Yeah. So like what this means is that, if for example, if your A and B are if your A and B are intersected, then the intersection in the A and the B counted as one area. So if A and B are separate, then you can just add the probability of A and B. But if there's an intersection, you do realize that if you just add A and B, right, you have the intersection counted twice, because it is both in A and in B. So in this scenario, what you do is to minus one of those things off. So the probability of A union B is probability of A plus probability of B minus the probability of A intersection B. So that is how you do this particular one. And the final one, of course, is the one that I was talking about, the one most related to conditional or independence, for that matter. So probability of A, I don't know how to say this. Probability of A given B. That's what it means. Yeah, sorry. Probability of A given B, that would be equal to the probability of A intersect B over the probability of B. So let me just dissect this for a second, because I'm pretty sure some of you might not have gotten this even after your lecture. So let's just dissect this for a second. Okay, so the thing that we are calculating here is the probability of A given the occurrence of B. So you must take note that in this scenario B has already occurred. You know what I mean? Yeah. Let's say you have a red and blue scenario. Let's say the event B is taking blue and event A is taking red. So let's say you took one blue already, like the first step. So now your probabilities have changed already, right? You can't just use the 3, you can't use the 9 or 13 and 4 or 13 anymore. So how do you calculate the probability of taking a red given that you took a blue already? So the first part is the intersection of A and B. Because the reason is because both events are happening in the sense. Of course, in our red and blue experiment, we don't really have that much of an intersection because actually there's no intersection because they're mutually exclusive. Wait a minute. Hmm. Then is the probability of A given B 0. Okay. Oh, okay, wait. Okay, sorry. In this scenario, we are looking at red in the second one and blue in the first one. Sorry. That's why you still have an intersection. Otherwise, it wouldn't make sense. If you were to look at it as taking a red and taking a blue without saying when exactly you took it, then obviously they're mutually exclusive events. But taking a red in the second one and taking a blue in the first one are not necessarily mutually exclusive because they can happen at the same time. You can take a blue in the first one and then a red in the second, or vice versa, whatever I just said. I don't know what I just said. Okay, fine. But you get the point. Therefore, there's intersection. And so in order for this to work, the events must not be mutually exclusive. If they're mutually exclusive, then this is already zero. This doesn't work. Like this will be zero in a sense. So why do you then divide it by probability of B? So if you have your intersection, we got the reason for that. Because they are not mutually exclusive, they must both have a chance of happening in the sense. Together, that is. For one to actually influence the other. So you're dividing it by the probability of B, because if you think about it, if the overall probability of getting both the red, like A and B together, which is basically the A intersect B, is to multiply probability of A happening and then multiply the probability of B, probability of B happening and then multiplying the probability of A given B. So the best way to approach this is not the way that is written in the syllabus, but more of the way that more of the written in the form of P A given B times the probability of B is equal to the intersection of A and B, probability of A and B. So yeah, that's how it works actually. That is just how it works. And therefore you get this particular equation. It makes sense in the way that I see it. And therefore you can freely use this equation as long as you know that this is a conditional probability and the events are not mutually exclusive, because if they were, the probability of A given B is 0, the probability of intersect B is 0, and you get the idea. But you can still use it if it's 0, you just need to know that it's 0. And I hope that helped you. There'll be some questions that look a bit more abstract. They just give you the the value of A, probability of A given B, and you need to calculate something else. So you can just do it now, now that you know how all the equations work. And if in doubt, just draw a Venn diagram or tree diagram or something. I don't know. That's the best way to tackle probability sometimes. Just draw diagrams or take cases, like take each of the cases. Because honestly, even I mess up a probability question many a times actually. And in most of the times it's because you miss out on one of the cases that you didn't even take note of. And it's very important to be very careful with which techniques you use in terms, and like which stuff you need to take note of. when you're doing probability. So yeah, I wish you luck in doing the probability questions. And if you want a video on how to do the math, like doing the math exam in general, I will do that next week instead of going to the next topic. Or I'll just do it as a separate extra video maybe if you want. If you do not want that, then I'll just move on to the next topic next week. So yeah, if you want to actually participate in the decision of the next video, please like say something in the comments, or if I decide to post a question, a poll or something, just answer that. Okay. I hope I hope you understood this topic. Good luck for A's as usual. And with that, if you enjoyed the video or found it useful, please press the like button and subscribe. Then I would like to say thank you and bye.